what is all of this? This is power. And power is what I want to talk to you about today. But before we can talk about statistical power, there's something that we need to cover first, and that is making mistakes. In inferential statistics, you are going to be making a decision about a population of interest based on your sample data. But some of those decisions you make could be wrong. Let's go take a closer look, shall we? Let's say you're looking to compare two populations to each other. You sample each population, and based on the statistical test you use, you decide that the two populations are different from one another. If, in reality, the populations are different, that's great. You have made a correct decision. However, if you decide the two populations are different when in reality there is no difference, you have made a mistake, and this mistake is called a type 1 error. To be clear, you can only make a type 1 error when you reject the null hypothesis and state that there is a difference between populations. What if, based on your sample data, you decide that there is no difference between the two populations? Well, if there really is no difference between the two populations, then you have made the correct decision. But if you fail to find a difference when in fact the two populations are different, well, now you've made a different kind of mistake, and this type of mistake is called a type 2 error. Type 2 errors only occur when you fail to reject your null hypothesis. Look, I don't want to make a mistake. I don't want to make one of these kinds of errors. But how do I protect myself? Whenever you read the results of a study in the primary literature, you see a p-value associated with the concluding statements being made. For example, a paper may conclude that among the extender components examined, post-thaw sperm motility and forward progressive status were lower in DMSO versus glycerol-based treatments, p less than 0.005. P-values come from measuring the area under a probability distribution, thus they can range from 0 to 1. The p-value is a conditional probability. The condition is that there is no difference between the populations. The p-value is the probability of observing the difference between the two samples you measured, or a difference even more extreme, just due to chance alone, given that the populations are actually not different. Thus, the p-value measures the probability of committing a type 1 error. The most commonly accepted type 1 error rate, otherwise known as alpha, is 0.05, or a 5% chance of committing a type 1 error. Thus, researchers protect themselves by only rejecting the null hypothesis and declaring a significant difference when p is less than 0.05. Phew! But what about type 2 errors? How does a researcher protect themselves from making one of those? You know what? I know the answer. The answer is power. The probability of committing a type 2 error is called beta. Power equals 1 minus beta. Therefore, if there is a true difference between two populations and you increase power, you will decrease beta, or decrease the chance you commit a type 2 error. So how does one increase their statistical power? Experimental design plays a huge role in trying to maximize statistical power. For example, you may choose to use very homogeneous experimental units, limiting the amount of random variation that is observed between units. Another strategy would be choosing treatment levels that are more different from each other, for example, comparing plant growth at 25 degrees to 35 degrees versus using 25 degrees and 28 degrees. Increasing sample size, or the number of experimental or observational units, also increases statistical power. In general, you should design your experiment or study to have 80% power or more. But how do you know how much power your study has? This is where power analysis becomes important. But what is it exactly? And why should everybody be doing it? Power analysis is most often used to determine the sample size required to detect a difference or effect of a given size with a certain amount of confidence. If you are writing a grant application, it will often be necessary to perform a power analysis in order to justify your sample size to reviewers. This is particularly true when your study uses animals or human subjects. It can also inform you whether or not it is worth pursuing a particular study, because you may find that you will need an unreasonably large sample size to detect the effect you are hoping to measure. Power analysis is performed using the relationship between 5 pieces of information: sample size, magnitude of the difference between populations or effect size, the amount of natural or random variation that exists within the population, the acceptable level of type 1 error, or alpha, and power. In order to perform a power analysis, you will need all but one of these pieces of information from which you can calculate the one that is unknown. I personally recommend you use a statistical package to perform your power analysis. In some cases, you may make your best guess about one of these necessary pieces of information, for instance, the estimation of the variance. It is good to perform a literature search to see if you can find information about what you hope to measure, or if possible, you can always conduct a small pilot study to collect some preliminary data which may help you inform your larger study. Hey guys, there's a link to my blog in the video description below where I go through an example on how to do a power analysis for a study where the data are analyzed as a 2-sample t-test. I'd highly recommend you go and check that out. Also, if you'd like to see more videos like this one, be sure to subscribe. And if not, I might just have to come beat you up.